Assalamualaikum and greetings everyone. It's right now it's 4:29 a.m. Okay, right now it's in the morning. So today I would like to teach you all about the damp oscillation, the lecture 6, 4.3 physical discussion. But before we go into further about the lecture 6, I would like to do some revise to some of you. Okay, so let's go back. Okay, let's say that we have a spring here and it is attached to a block, and here we have the simple harmonic motion. Okay, simple harmonic motion case. Okay, and here, hold on, sorry, I did not ready here. So right here we have the equilibrium position in the middle. Okay, and assume that, okay, right now the object is moving to the right. Okay, the velocity here, and of course we have the displacement right here, which is x equal to, not equal, it should be more than 0, right? More than 0. Okay, so here in the simple harmonic motion, okay, we have a spring attached to a block, and at the same time it is on the ground. Okay, on the ground, it is on the ground. So in simple harmonic motion, remember that there is no friction, and at the same time there is no energy dissipation. Okay, which means there is no loss of energy. And the third is that total energy is conserved. E total is conserved. So let's look on the force distribution of the system. Okay, so in simple harmonic motion, remember that there is no friction or there is no resistance acting on the system. So what are the force that acted on the system is only one, which is, we called it as the restoring force of the spring, which is Fs, right? See that, as you can see, as the block is moving to the right, there is a force that is opposed the direction of movement of the system, which is directed to the left. Okay, so here, as we can see that the force is directed to the left, that means it is negative. So negative Fs, which is negative restoring force, is equal to ma, of always related to the second Newton's law's equation. Okay, and then we know that Fs is equal to negative kx. So negative multiplied with negative kx equal to m, and then a is acceleration, which is represented as the x double dot, and then at the end we know that kx equal to mx double dot. So here is what we call the force distribution of the system, and at the end we get that kx minus mx double dot equal to 0. Okay, that's pretty simple. Okay, and then every one of them will divide it with m. Finally we get that kx over m minus with x double dot equal to 0. So the acceleration of the system, so x double dot is equal to k over m x. Okay, so simple over here. So here is the acceleration of the system, and when we know that k over m is omega square, right? Because we know that omega is equal to square root of k over m. So the square root will transfer to the left, so we get that omega squared is equal to k over m. So finally, x double dot is equal to omega square x. Notice that the acceleration of the system is positive. It is because the system is moving to the right. So that means when the object is moving to the right, which means that the object is accelerates to the right. That's why we get that the acceleration of the system is positive. So we have the acceleration positive right here. At the same time, we have the velocity, which is x single dot, is also positive. Okay, pretty simple, right? Okay, now let's move on to the actual reality. Now let's look on the reality. Now here is the reality. Okay, same case. Okay, we have the string here. Okay, and then attached to a block. Okay, and of course it is on the ground. So for this one right here, okay, in reality, we know that there is a frictional force. Okay, frictional force. Okay, first let's look on here. So we have the wave here. We have the wave shape as this one, but we're not going to touch about the y component force. Okay, acted on this object. We're going to look at the force that is acted on the x component. Okay, so here in here, okay, assume that. Hold on, let's look up here. This is equilibrium position. So assume that this object is moving to the right. Okay, moving to the right. So here, at this point, there is two forces acted on the system in reality. So the first force acted in here is, of course, the first one is the restoring force. And at the same time, there is a force which is also directed the same with the restoring force, which is, we call it damping force, which is F damp. Okay, so we have the Fs equal to negative Kx, and at the same time we have the F damp, which is the damping force, is equal to negative gamma x single dot. Here is equal to damping force, which is also known as, we call it as the resistance force, which makes the object to stop oscillates at a particular time. Okay, so notice that the force here is negative, right? The F damp. So which means that although the object is moving to the right, which is here is equal to x dot, single dot here, although the object is moving to the right, at the same time there is a damping force that is actually directed opposite to the direction of the object, the system here. So that's why we have the negative at the early of this equation here. Same with the restoring force here. Okay, so this force is important that you should memorize, because it will relate to our derivation of formula here. So let's move on to the force distribution here. Oh, hold on, before that. So in this reality, we know that there is friction, which is friction is actually damping force right here. And of course, when there is the friction in the system, of course the object will stop oscillates at a certain time, right? The object will slowly stops moving. So that means this object, the energy here will dissipate, which means that the energy there is loss of energy. This one should be remembered. Okay, and the last one, the total energy is not conserved. Okay, this is a third point that is really important when the questionnaire asks what happened in the reality, exactly what happened here. Okay, let's move on to the force distribution. This is the force distribution. Okay, so force distribution, since that the object is moving, that means there is an acceleration in the system. Okay, so of course first we have to equal to ma, because the object has an acceleration. Okay, the system has an acceleration right now, since the object is moving to the right. Okay, and at the same time we have the force, which is negative Fs, and then minus with F dam here, F dam. Right, so let's break through the formula here, which is negative kx minus with the negative gamma at single dot equal to and then a, we change it into x double dot. Okay, now what happened is we get that kx plus with gamma at single dot equal to mx double dot. And now we move to the left here, so we get the kx plus gamma at single dot plus with the mx double dot equal to 0. Okay, now every one of these formula, each of these formula will divided with m, divided with m, divided with m, divided with m, divided with m. So finally we get that k over m times with the x plus gamma over m times with the x single dot plus with the x single dot equal to 0. So here we know that k over m is equal to omega square. So this is omega square. Oh sorry, omega naught. Okay, omega naught. Since that the system is changing, okay, we in this reality we apply a simple harmonic motion equation, and at the same time we put some modification. Okay, we put some modification that change the exactly what happened in the simple harmonic motion. This is now we look on the reality of the equation. Okay, so this is omega naught. So what happened? We get that omega naught square x plus with the gamma over m x single dot plus x double dot is equal to 0. Now I will do some rearrangement here, so we get that x double dot plus with gamma over m x single dot plus with the omega square x equal to 0. Okay, this one right here is what we called it as the where's my pen? No. This one right here is what we call is the differential equation of damped oscillation. Okay, why is this called is differential equation of damped oscillation? Because this equation is actually, okay, this is actually what happened. This is actually d2s over dt square plus with gamma over m times with the dx over dt plus with omega naught square x equal to 0. This is exactly what is the differential equation of damped oscillation. But to ease up the understanding of us, we can use this one as the differential equation of damped oscillation. Okay, now let's move on. Okay, let's move on to the next one. Now let's go to the 4.3 physical education, physical discussion. So okay, let's move on. 4.3 physical discussion. So in the previous lecture, okay, there is 3 cases related to damped oscillation, and each one of them have a different form of displacement equation, right? So here we have 3 cases here. So this is case 1, this is case 2, this is the last case. case 3. Okay, so this is case 1, this is case 2, this is case 3. Each case has its own physical properties. Okay, for case 1, okay, we know that gamma is equal to 2m omega naught, right? So it is critically damped. Very simple. Okay, now let's move on to the second case. We know that gamma is more than 2m omega naught, right? So that means this case is over damped. Okay, now for the last case, we know that gamma is less than 2m omega naught. Okay, which means that this case is under damped. Okay, simple. Now at first, right now, or before we go further, okay, let's write the displacement equation for each of these cases. For the case 1, which is gamma equal to 2m omega naught, so the displacement for this case is xt is equal to exponential power of negative gamma or omega naught t, and then times with the c1t plus c2. And for the second one, xt is equal to exponential power of negative gamma over 2m times with the t times with the beta 1 exponential power of qt plus with the beta 2 exponential power of negative qt. Okay, and then the second one is xt is equal to a naught exponential power of negative gamma over 2m times with the t, and then times with the sine omega t plus pi. Each one of it is really important. Okay, and here we will change the here to xt equal to exponential power of negative gamma over 2m times with the t times with the c1t plus c2. Why change it to a gamma over 2m? It is because we know that gamma is equal to 2m omega naught, right? From the first case right here. So what happens if we change here is that gamma naught is equal to gamma over 2m. So that is why we change gamma omega naught as a gamma over 2m from here. Negative omega naught is equal to negative gamma over 2m. Okay, so why do I do that? It's because each one of them has an equal exponential equal to gamma over 2m here. Negative gamma over 2m. Every one of them. So I want to show you how clear is it. Okay, so first right here I will show you the case 3. Okay, this is the easiest one to explain. Okay, so let me go pencil here. Okay, right now before that I'm going to show you what it looks like for the simple harmonic motion case. Okay, so here we have a graph here, right? And here is the x, and we have a graph over here, which is right here is t. Okay, so here in centimeter or maybe meter, right here in second. So for the simple harmonic motion, we know that it oscillates non-stop and there is no dissipation of energy. So what happens is this is what it looks like. from here we see that, okay, from here we see that, okay, we see that this graph is perfectly oscillates in simple harmonic motion. So here is the positive amplitude and here is the negative amplitude. So this is what we call the graph is as the xt equal to a sine omega t plus pi naught. Okay, now let's compare with the equation of the underdamped. Okay, so let's see. So xt is equal to a naught exponential power of negative gamma over 2m times with the t times with the sine omega t plus pi naught. Okay. So in this graph, okay, like I said, okay, this is the graph for the simple harmonic motion, right? So in simple harmonic motion, there is no damping force. When there is no damping force, we know that damping force is equal to negative gamma times with the velocity. Since that we don't have a damping force, at the same time there is no damping constant, which means that damping constant is equal to 0, right? Damping constant is equal to 0. So when we substitute gamma inside this equation, okay, right now I'll do some substitution. So xt equal to a naught exponential power of, so gamma is equal to 0, which is 0, and then over with the 2m, okay, and then times with the sine omega t plus, since that we have the oscillation is start at the x equal to 0, so that means the pi naught is equal to 0. So here is when gamma is equal to 0 and I naught is equal to 0. Okay, so this is special case. So when we do that, we will actually get that. So xt equal to a naught times with the exponential power of 0, right? Because 0 over 2m is equal to 0. Okay, now times with the sine omega t. So finally we get that. We know that exponential power of 0 is equal to 0, right? Equal to 1, sorry. So finally we get that xt is equal to a naught sine omega t. So this actually represents back to the simple harmonic motion. So this is the proof that the system is oscillate in simple harmonic motion. Now, what happened when there is a damping constant? What happened to the oscillation of the graph when there is damping force? Okay, so notice that in the limits of the gamma, we want to have the damping constant is less than this quantity, which means it should be 1 over 8 or maybe 1 over 4 or maybe 1 over 2, which is not exceeds more than 2. Okay, so I'll show you a graph here. So here is the simple harmonic motion, right? So let's look on the reality. Here, reality. Okay, so we have the same right here, which is xt, and sorry, that's centimeter, and then we have the t at the time second, measure. Okay, now we have the graph. Sorry, before that, okay, let's write the equation for the damped oscillation. So xt is equal to a naught exponential power of negative gamma over 2m times with the t times with the sine omega t plus pi. Okay, Now, since that the in reality there is a damping force or resistance in the oscillation system, so that means that the system will not oscillate just like simple harmonic motion right here. So it will change a bit. Okay. So what happens that right here, let's compare to the simple harmonic motion equation. Okay. So we have the xt equal to a naught sine omega t plus pi naught. Okay, let's look at the first one right here. Okay, this right here is what we call the amplitude, right? And this right here, we don't call it amplitude. We change it to time dependent amplitude, which means that this displacement in reality, it will reduce over time. Okay, or we call it the amplitude of the system will reduce exponentially. Okay, right here, so the amplitude of the system will reduce exponentially, or A will fall back to 1 over E. Okay, so what happened here is that since that there is a presence of the exponential in this graph, okay, that means that this graph will reduce exponentially. Okay, so here we have the exponential graph, which is acted like this, and here the other side too. Alright, now I'll draw the graph. So this is what happened in reality. Okay, so that the systems will oscillate. Okay, the system will oscillate slowly. Slowly reaching equilibrium. Okay, so notice that the equilibrium of this notice that the amplitude of the system will reduce exponentially. This is what we call reduce exponentially. At the same time, the amplitude of the system reduce over time, which means that as the time increases, the amplitude will reduce. Okay, that's what happened. So here, this one right here, the dotted line here is equal to a naught exponential power of negative gamma over 2m times with t, positive, right? Positive. And this right here is negative a naught exponential power of negative gamma over 2m times with t, which is in negative. So they have the both side here. We have the we have the time dependent amplitude on the right side, and we have the time dependent amplitude on the opposite side here. So this is what happened when the system is under damped. I will give you some the example of the pendulum, simple pendulum. Okay, so simple pendulum. Let's say that we have the string strict on the ceiling. Okay, here we have the equilibrium position right here. This is equilibrium position, and we have the system. We have this. We have the pendulum right here. Start from here. Okay. So what happened that? Let's say that the pendulum starts moving to the left. Okay. So what happened here that when the simple pendulum starts moving, in reality, okay, it will start moving like this, like here, and suddenly at a certain time, it will start to slowly oscillating and stop at the equilibrium position. Okay, I'll show you right here. Show here, and then start this slowly, and stops at the middle, which is the equilibrium position. Hold on, I'll give you some example right here. give you an example right here. Right here. Okay, let's say that this is the pendulum here. So it starts to move like here. I pull this pendulum right here, and then start moving, and suddenly the pendulum start to slow down, and then it stops at the middle, in the equilibrium position. So this is what we call that the system oscillates in under them. Okay, this is what we call the case is under them. Okay, very simple, right? So what actually happened here is that the system starts to lose energy. Because of the friction force or the damping force. Okay, so here what happened is that hold on, what should I write here? Let's write over here. Okay, so what happened exactly is that, okay, what happened in the under damped oscillation, says that, okay, the system starts to lose energy. Okay, it starts to lose energy. So when it says that start to lose energy, why? It is because of the presence of the damping force. This force is the reason why the system losing energy, and at the same time, this force is the reason why the system is in equilibrium at the end of the oscillation. Okay, because of the damping force, start losing because of the damping force. Now, this lost energy is, we talk about the total energy, E total. Okay, E total. So we know that E total is equal to K plus U, which is kinetic energy plus with the potential energy, and at the same time is equal to 1/2m omega square A square. Okay, this is at the end of the derivation of total energies formula. Okay, so notice that we have the A square, we have the total energy. So as the amplitude of the system decreases, right here it starts to decrease, right? So as the amplitude is decreases, so that means the total energy will lose over time. As the times increases, the amplitude decreases, and at the same time the total energy will decreases. That's what it means. Okay, so let's talk about the period of the system. But before we talk about period, let's talk about the angular frequency, about omega. So we know that omega is equal to 2 pi over t, right? And for this system, to calculate the omega, the frequency, we know that it is equal to omega equal to square root of gamma square over 2m. I'm sorry if I'm wrong. Okay, gamma square over 4m minus with omega naught square, right? And here omega naught is equal to square root of k over m. So that means that this omega right here, okay, this omega right here, we have the quantity here, and then we have to minus it with the origin, with the natural frequency, angular frequency. So that means that omega is less than omega naught. So what happened when omega naught is less than omega naught? So let's compare here. So we have omega naught equal to 2 pi over t naught. Okay, right? So when it says that the omega is less, right? So that means that the period is more, right? So that means that this system takes more times to complete oscillation. Okay, which means that this system takes more times to complete oscillation. Okay, I'll show you the example here. Okay, let's say that we have the simple harmonic motions oscillation system. Let's say that this one takes around 2 seconds. Okay, but for the damped oscillation, it takes maybe more than 2 seconds. Okay, maybe it should be 2.5 seconds. Why? Because the omega, okay, the omega right here is less than omega naught, and at the same time the period of the damped oscillation is more than period of the simple harmonic motion. That's why it takes more times to complete one or two oscillations than the simple harmonic motion. Okay, I think that's clear for you all. Now let's move on to the first case, the critically damped. For this case, okay, right now we have a case that we increase the quantity of 2m omega naught. Okay, we increase the quantity of damping constant. Right now, before this we have a damping constant that is less than 2m omega naught. Now let's see what happens if the gamma, or the damping constant, is equal to this quantity. So what happens is that the system, so this is x at the time in centimeter, and here in the second, so in second. So what happened that, okay, this system will actually not oscillate. Okay, let's say that the system is oscillating, right? Okay, we have here, and then suddenly it's fall back to equilibrium right here. Okay, right here, and closely to the equilibrium. So what happened exactly here is that, okay, the system is critically damped. This is what it calls. And at the same time, okay, this system is actually not oscillating. This is actually not, we call it as oscillation, because it is not completely one, it does not complete one oscillation. So this is why we call it, this is actually not oscillating. So this right here, okay, let's imagine an absorber, okay, a car. Okay, let's move in a car. Let's imagine a car. Okay, I don't know if you guys ever watched WRC, which stands for the World Rally Championship. Okay, let's say we have a car right here. Okay, we have a car right here. Okay, yeah, okay, please don't judge my drawing. Okay, yeah. Okay, now we have a bumpy road, or maybe we want to jump. Okay, let's say that the car is jump. Okay, we have a ramp here, and then the car start to jump, and boom. Okay, it lands on the ground. So what happens that in the absorber, we have the absorber in the car, okay, right here. So what happens that when we land on the ground, okay, what happens is that the spring right here will absorb the amount of impact on the jump. Okay, what happens is that the spring will gradually increase the amplitude. Okay, and then you know when the car jump and then land right here, and then suddenly it goes up, right? So when it being pressed down, okay, it's being pressed down. Now right now the graph shows that the spring is decompressed. So it's being pressed down, and then it starts to go up, right? Jump and then land. It goes down. The spring goes down, and then when it comes to the recovery, it goes up. So this is where we call it the critically damped. Okay, so when the spring is being goes back up, okay, so we are here, goes back up at the maximum amplitude right here, and then suddenly it starts to recover to the equilibrium position. Okay, it's like boom, walk like that. So when you, I don't know if you ever experience this, what should I say? Okay, imagine that the car is hitting a plug hole. Okay, a plug hole. Okay, what you feel is that it starts to hit the plug hole, and then the spring goes down, right? We hit goes down, it goes, the spring goes down, and then at the same after at a certain time it goes back up and then stop. This is actually what happened. It goes down. Okay, here we have it right here. We have goes down here. It goes down, and then goes up, and then back to the equilibrium position. That's it. So this is what we call the system is critically damped. Okay. Hold on. And we have that the gamma. We have the exponential power of negative gamma over 2m. That means that the system is how do I say this? It reduce like this. This is exponential. This right here is where the exponential power of negative gamma over 2m. Okay, so this is what happened to the system, and at the same time this system does not overshoot. It just that this system, it does not overshoot. It's just like it goes positive and then that's it, goes to the equilibrium. It does not go up and down, go up and down, up and down. That's it. Okay, so this is what we call the system is critically damped. Okay, I think that's clear for you all to explain that. Okay, now let's move on to the overdamped system. So for the overdamped system, we know that the damping constant is more than the quantity needed here. So here we have the graph right here. So sorry, now I'll show you the difference between the two quantity. Okay, so we have right here and right here. Okay, we have two. So the first one is start move up here and it goes down, and then up here, and we have another one which is goes up here, and then slow down this side right here. So we have a graph which is hits up here. Okay, so this is when gamma is equal to 4m omega naught, and here we have a graph here which is gamma equal to 8m omega naught. Okay, as you can see, we have a different amplitude right here. So we have the A1 and A2, right? So for gamma equal to 4m omega naught, this is for A1, and we have a gamma equal to 8m omega naught, this is A2. Okay, so each one of them have the different amplitude reach out. Okay, how do I explain this? For this system, okay, since that we have increased the damping constant, okay, what happens that when we increase the damping constant, gamma increases. Okay, so that means that the damping force increases, right? So that's the first case, and we know that F damp, which is the damping force, is the resistance. So since that the resistance increases, that means that resistance increases because the first one is the gamma, okay, and the second one is because of the velocity, right? Because F damp is equal to negative gamma times the velocity. So this is the reason why the resistance is increases. So right here, as the what's it called? As the damping force increases, okay, we will produce a huge amount of amplitude, which is when gamma is increases, that means the amplitude from equilibrium increases, right? So this is what happened here. So no, so cancel that. Number 2, when damping constant increases, okay, what happened to the amplitude is that it provides, okay, sorry, did I make a mistake right here? No, sorry. When we provide a huge when we provide more damping constant, okay, that means that the amplitude produced from the system from equilibrium, which is amplitude from equilibrium right here, the amplitude from equilibrium right here, this is amplitude, so it takes much more less, it takes more or less when we increase the damping constant, right? So that means the amplitude from equilibrium is decreases. Or let's say I write right now I put 4 right here. Now let's put 6, okay, 1 up to 6, so 6 should be like this, should be more than this, and then increase like this, okay. So this is gamma equal to 6m omega naught, okay, it's simple, right? Okay, so when damping constant increases, okay, right here, so what we see that the amplitude from equilibrium will decreases, okay, and at the same time when gamma is increases, okay, what happens is that the time to approach equilibrium takes more times, okay, which means that it becomes slow to approach this equilibrium. This is right here is what we call the equilibrium condition. Okay, what is the example case for this one? Then I'll show you the example right now. Okay, hold on. So here is the example of the overdamped oscillation right here. So we have the door right here, okay. So what happened is that when we apply amount of huge amplitude right here, okay, this is equilibrium position, and we have the amplitude which is about I don't know how much is it, okay. So what happened when I release the door, okay, right now I want to make the door to shut down right here, which means I want to make the system to go back to equilibrium, okay. When I release the door, okay, it takes long time to reach equilibrium. Okay, this is one of the example of the overdamped oscillation. Same as this one too. See that the door has the shuttle door here. So you open the door and close it. See that the object takes a long time to go back to equilibrium. That's the another example of it. So the conclusion is that, okay, for the case one, it is oscillation. It is oscillation, okay. It is what we call oscillation, okay. And how do I say? For the case, sorry, not case one. Sorry. Case another. Okay. For case 3, okay, this is what we call oscillation. Okay, oscillation. And at the same time, this is what we call that the system is too springy. I mean, like, you know that the graph of the system is like slowly approaching equilibrium. I'm sorry, the system the amplitude of the system decreases exponentially, like it should be like this, and then suddenly stop at the equilibrium. So this is what happens when the system is too springy or underdamped. This is underdamped. Okay, and yeah, it's good. Okay, and for the case 3, again, the total energy will reduce over time, same as the amplitude of the system. Okay, same as the amplitude of the system, reduce over time. Okay, and what should I say? And the third one, that the period of the system is more than the period of the system in simple harmonic motion, which means that it takes more time to complete one oscillation. Okay. Now for the case 2, for the case 1, which is critically damped. So the first state is that it is not oscillate. It is not oscillates. Okay. So and then the second one is that it is not oscillate, but it will asymptotically approach equilibrium. Okay, we know that the graph is like this, right? This is a graph. So we know that this is the equilibrium here, right? So the graph will asymptotically approach equilibrium. So this is the graph here, and at the maximum here, and then suddenly, reduce, and then it will asymptotically approach equilibrium. It will not equal to 0. Okay, which means that this system, okay, will not equal to 0 over time at the particular time, but it will just approaching 0. It will not equal to 0, but it approach to 0. Okay, that's what it means. But and at the same time, it will asymptotically approach equilibrium as fast as possible. Okay, so that is the case 1. Now let's move on to the case 2, which is the last case, which is overdamp. Okay, so for overdamp, again, it is not oscillates. Okay, and at the same time, but okay, it will asymptotically approach equilibrium, but slow. Okay, but slow. That's what it is. But slow, but this one is as fast as possible. That's the difference. Okay, and we know that when gamma we call it the damping constant increases. Okay, that means F damp, or the damping force, increases, right? So when F damp increases, that means the resistance increase. And resistance increases due to gamma and X single dot. So that means the faster the object move, the more damping the faster object move, the more damping force apply on the system. Okay, that's what it means. So and then when resistance increases, okay, when the resistance increases, that means that the gamma, the amplitude from equilibrium will decrease. Okay, will decrease. It's like a how do I say this? It's like when there is so much resistance, okay, it cannot oscillate much higher. How do I say that? It cannot produce a much more amplitudes, because there is a force that drags the object to oscillate more. Okay, let's say that we want to hold on. Let me think for example. Let's say that we have a spring here. Okay, we have the spring here, vertically spring. We have a block of vertically spring. Okay, let's say that the object is moving downward. Okay, V right here. When that is when the damping constant increases, the damping force increases. When damping force increases, the resistance increases, which means that at the same time it will produce it will produce less amplitude because of there is much more F damp here, which makes the object to produce low amplitude. That's what it means. And when at the same time, when resistance increases and amplitude from the equilibrium to equilibrium here, so when we have the damping force increases, or which are equal to resistance here, the more resistance, the less amplitude it produces. Alright, okay, at the same time, okay, it takes more time to reach equilibrium or approach. Why? Because when the object, okay, this is before. Now let's look at after. Okay, so we have a sink here and a spring here. Okay, now we want to go back to equilibrium, right? Right here, right? This is equilibrium. Now we want to make the object to go back to equilibrium. Of course, the damping force is acted opposite to the movement of the object, which is F damp. That's why the object takes more time to reach equilibrium. It takes more time to increase equilibrium. That's what it means. Okay, so I think that is all for today. Thank you for your attention, and I hope we see you again in the next day. Goodbye and happy study. Ciao ciao.